All right, let's dive into a classic coding puzzle. It's one of those problems that looks pretty simple on the surface, but it's hiding a really beautiful and elegant solution. Honestly, it's a perfect example of how just a small shift in your thinking can totally unlock a problem that seems tricky. Let's get into it. So here's the game plan for today. We're going to start by laying out the challenge itself. What are we trying to solve, and what are the rules? Then we'll look at the first idea most people have and, why it's a total trap. After that, we'll uncover the key aha moment, walk through the brilliant two-pass solution, and finally, really appreciate what makes it so dang efficient. Okay, first things first. Before we can solve anything, we have to know exactly what we're being asked to do. And in this puzzle, believe me, the rules of the game are everything. So the goal itself sounds pretty simple, right? You're given a list of numbers, and you have to create a new list. For every spot in that new list, the value should be the product of every other number from the original list. So if your input is, say, 1, 2, 3, 4, the very first answer you're looking for is 2 times 3 times 4, which is 24. For the second spot, it'd be 1 times 3 times 4, which is 12. And you just keep doing that all the way down the line. But here come the constraints, and these rules are what make this a real puzzle. First, it has to run an O(n) time, which basically means we can't get bogged down in nested loops. We need a linear time solution. But here's the real kicker. You are absolutely forbidden from using the division operator. That one rule just changes everything. So when you're faced with these rules, especially that no division one, your first instinct might lead you down a path that seems super logical, but it's actually a dead end. Let's explore that common trap. The first thing that probably jumps into your head is, okay, why don't I just calculate the total product of the whole array? For our example, 1, 2, 3, 4. The total product is 24. Then, to get the answer for each spot, you'd just divide that total by the number of that spot. So for the first element, 1, the answer is 24 divided by 1. For the second element, 2, it's 24 divided by 2. It seems so simple and so logical. But this simple idea fails for two massive reasons. First, and most obviously, it flat out breaks our most important rule, no division. But even if you could use division, this whole approach has a fatal flaw. What happens if your array has a 0 in it? The total product instantly becomes 0, and then you can't figure out the answers for the other spots because you'd have to divide by 0, and the whole thing just falls apart. So that easy path is completely blocked. And that means we need a totally different way to think about this. We have to reconsider what the product of everything else actually means. And this right here is where the light bulb goes off. Okay, let's try to look at this from a different angle. Instead of thinking about the total product of the whole array, let's just focus on one single position. Let's call it index I. What information, if we could get it, would give us the product of everything except the number at I? And this is the key. This is the whole trick. The product of everything except a number at a certain position is just the product of everything to its left multiplied by the product of everything to its right. This idea is so powerful because it completely sidesteps the need for division. It breaks the one big problem into two smaller pieces that we can actually calculate. So, how do we actually turn that insight into code? Well, if we need the product of the left side, and we also need the product of the right side, that kind of suggests a strategy where we'll need to go over the array in two different directions, doesn't it? And that leads us straight to the two-pass strategy. In our first pass, we're going to travel from left to right. For each position in our answer array, we'll store the running product of everything that came before it. Then, we do a second pass, this time from right to left. And for each spot, we'll multiply the value we already stored there by the running product of everything that comes after it. Now, theory is one thing, but this is one of those algorithms that really clicks when you actually see it happen. So let's take our example, 1, 2, 3, 4, and trace it through this whole process. Okay, here's our setup. We've got our input array, nums, and we've set up an empty answer array of the exact same size. This answer array is where all the magic is going to happen over our two passes. All right, let's do our first pass, going from left to right. For index 0, well, there's nothing to its left, right? So we just put a 1 as a placeholder. For index 1, the only thing to its left is the 1 at the start of nums, so we put a 1. Now for index 2, we multiply everything to its left. That's 1 times 2, which gives us 2. And finally, for index 3, we multiply 1 times 2 times 3, and that gives us 6. So after this first pass, our answer array is holding all of those left side products. Now for the magic of the second pass, this time from right to left. We need a variable to keep track of the running product from the right, and we'll start it at 1. Okay, at index 3, we take the value that's already there, 6, and multiply it by our right product, which is 1. The result is still 6. We then update our right product by multiplying it by the number in nums, so it becomes 4. Moving left to index 2, we take the 2 that's there and multiply it by our right product of 4. That gives us 8. Now update the right product. 4 times 3 is 12. Next, at index 1, we take the 1 and multiply it by our right product of 12, giving us 12. Update the right product again. 12 times 2 is 24. Finally, at index 0, we take the 1 that's there and multiply it by 24. And just like that, we have our final correct answer.
So getting the right answer is one thing, but the real genius, the true elegance of the solution is how incredibly efficient it is. And that goes right back to one of those constraints we saw at the very beginning.
Remember that little rule that said the output array doesn't count as extra space? Well, this solution uses that rule brilliantly. Instead of creating a whole new array for the left products and another one for the right products, we do everything right inside that single answer array. We use it for the left pass, and then we just update it during the right pass. This means we use practically no extra memory at all, which we call O of 1 or constant space complexity. And that is a remarkably clever achievement. And because this whole algorithm just relies on multiplication, it handles all of those tricky edge cases that completely stumped our first idea. Got a single 0 in there? No problem. The algorithm correctly calculates the product for the zero's position and puts zeros everywhere else. Multiple zeros? The whole result array correctly becomes all zeros. It handles negative numbers and their signs perfectly, all without ever coming close to a divide by zero error. It's just robust. And this really just wraps it all up perfectly. The magic is in that reuse. It's not two totally separate calculations. It's one clever, two-stage process that builds the final answer in the most resource-efficient way you possibly can. So this leaves you with a really powerful idea, right? This pattern we've just seen, a forward pass to gather one kind of information, followed by a backward pass to combine it with another kind, is an incredibly useful problem-solving technique. It really makes you wonder what other problems out there that seem impossible at first might just be waiting to be unlocked by this exact same two-pass approach.